Okay, let's continue with our discussion on picking out beam sizes or designing beams to support a load. We talked about last time about sizing the beam, getting the right size to handle a moment, an applied moment, and then checking the shear. So basically making sure both those constraints hold. There's a third one that's probably just as important, maybe more so, and that is the idea that deflection, or how much the beam is bending and moving, is as important or more so than the moment and the shear. Uh, so here's a diagram that I have with a beam that's cantilevered. I have a force F on the outside of it, and I'm saying X is pointing to the right. Notice I have this new variable, deflection, which is a lowercase v. So I know we have v for shear, and I've been using an uppercase V for shear. Now we have a lowercase v for deflection, and I don't make this up. So hopefully you can keep all that straight. But we're talking about this vertical direction being this lowercase v or deflection, and you can imagine if I apply this force, this green line would be what the beam looks like as it deforms, right? And we call that shape the elastic curve. So the elastic curve is what we're really concerned with. And in essence, what we're going to be doing today is developing an equation for that elastic curve, so that we could find the deflection, we can find the maximum deflection, we can do all sorts of things once we have an equation that represents that line. How do we get there? Well, if we define this lowercase v of x as the deflection, and deflection then is just that line. So we know if we take the derivative of that line with respect to x, that is what we're going to call theta of x, and I have it labeled up there as theta, and that is the slope. So we already know that the derivative of a line is equal to the slope of that line. Now, here's the next key part. If we take the derivative of that equation for slope, or the second derivative of my deflection with respect to x, that is going to have this new special thing. We're going to add this one other constant, 1 over EI. Remember, E is our modulus elasticity, I is our moment of inertia. So we're adding this extra little bit, and then this is going to be equal to the moment as a function of x. Now what this is called is the moment curvature function. And there is a relationship between the moment. If I take the derivative of moment, you may have learned this in statics. So now we're talking about the third derivative of my deflection with respect to x. That is, and I'm going to have to leave in this constant 1 over EI, but that's equal to an uppercase V, which we said was our shear function. And I can take the derivative of that, or the fourth derivative of the deflection with respect to x, leaving that constant 1 over EI, and that would be equal to my load function, or W of x. So why do we care? Because we want to get to here, the deflection, and we know certain things, like we know what the load is on our beam. If we know what the load is, I just need to work the opposite direction to get to deflection, or take the antiderivatives or the integrals as I move from load up to deflection. So, but here's the way we are going to do it. We are not going to go all the way from the load. Instead, what we're going to say is, let's just go from the moment up. And you'll see in a little bit, you could go all the way from the load, but I'm just going to cut to the chase. I'm cutting some content due to this whole change in the curriculum, and due to that extra day we spent on combined loading along with the extra long spring break, and just making this into one lecture instead of two, and actually just getting to the easier part. So what we're going to say is, if I can find an equation for the moment along the beam, then what I can do is I can integrate twice for the deflection. So what that looks like is, I can start with this EI constant. Now I'm moving it to the other side from what I had right there with the moment. So I'm going to say EI times the second derivative of my deflection with respect to x is equal to this moment as a function of x. Once again, that's our moment curvature. Then I can integrate that, so I would have EI dv dx, and that would be the integral of that moment function. Now, when I do integrate, it is an indefinite integral, and when you integrate an indefinite integral, hopefully remember this calc stuff, I end up with a constant of integration. And once again, this is the slope or theta of the beam. And then I can integrate again, and I end up with EIV, V being the deflection, is equal to the double integral of the moment with respect to x, and I end up with a second constant of integration. Of course, this is my deflection. So here's the fundamental issue with this, is that in order for that to work, I need one single function for the moment as I move from one end of the beam to the other. But if I think about a beam, let's say I had a simply supported beam with something like this, right? Or maybe even another load in here or something. I can't create a single equation because I have these discontinuities. I have one here and I have one here. So in this case, I would need 1, 2, 3 different moment functions, and I'd have to integrate them, and I'd need all sorts of different coordinate systems for each one, and it's a real pain in the butt. That's the information that I am eliminating from this semester's content. Instead, we're going to come up with this other method, and this method of coming up with a single moment function is called a singularity function. Now, I will tell you, it's also you'll hear these called discontinuity functions. And basically, the idea behind is this process will allow for a single or for one moment function, regardless of how many discontinuities you have. And the way they work, they're almost like switches. And we're going to define this new way of writing it. We have these brackets, and the bracket's going to look like this. We have x minus a to the n power. And also note that this is a bracket, not a parentheses. So the way these functions work, these discontinuity or singularity functions, is they're either on or off. And if we have x is greater than or equal to a, then this whole function can look like this. Now notice I do have parentheses, x minus a to the n power. And this is like that switch being on. However, if my x is less than a, then I have this whole function is just equal to 0, or it's off. So let's talk about the general process to find the deflection curve, and from there we can do a couple examples. I'll probably have to do that in a separate video because I don't want this to be too darn long. But if we look at this process, the first step that you're going to do when you have a beam is you're going to have to, just like always, you want to calculate your reactions. So you start off with your support reactions. After that, then your second step is to develop that loading function, or actually the moment function is really what we want. And this will be developed based on a table. And that's why most people like this method, because there is much less math involved. Instead, you're just looking up on a table. And it does say develop loading or moment. I'm going to focus on developing the moment, but I'll do one example where I do both from the load and from the moment. But the moment is generally what you're going to do. It's a lot easier to start at the moment. But before we get there, you probably have no idea what I'm talking about. What does this table look like? By the way, this table is found on Blackboard under Today. It's also under textbook images. You can find it there as well. So this is what my table looks like, and you can see I have different types of loads. So I could have a moment, I could have a point load, I could have a distributed load, and I could have a sloping distributed load. Each one will have a loading function. So this would say the magnitude of the moment. Note the direction. This is a clockwise direction, is positive in this equation. Then I have those brackets, and I have x minus a, where a is the distance away from the end, to the power of -2. And then my shear function, so this is the loading function. I could start there, and like we said before, I can integrate this, and I end up with my shear function, right? It's already done for you. The work is done for you. And I can integrate again and come up with my moment function. This is where I was saying you could potentially start either on this column or just start on this column. If you start on the moment function, it saves you 2 integrations. That's why I prefer to start at the moment. And I know as I'm saying a lot of words, I'm talking kind of quick, so you probably have no idea what all this means. I think when you see an example, it'll make more sense. So, but let's before we do the example, let's talk a little bit about the third step. After we have our moment function, the third step is to integrate for our slope and deflection. Now, when we're integrating the singularity function, we have to take into account one fundamental rule. And that rule is, if I look at my singularity function, which is like this, x minus a to the n power, if my n is less than 0, so n is negative, right? Then the integral of x minus a to the n power is equal to x minus a to the n plus 1 power. And the other option is if n is greater than 0, then what we end up with is the integral of x minus a to the n power is equal to x minus a to the n plus 1 divided by m plus 1. So this is our normal integration method, right? So if I'm integrating, say I'm integrating I don't know, x squared, right? What is the integral of that? It's equal to x cubed, and then I'm dividing by that exponent up there, right? So if you look, that's the exact same thing that we just said. So the only thing that's different, and by the way, this is going to be like what we're going to use 90% of the time, maybe even 99% of the time. The only time it's really different is if we have a negative exponent, then we just aren't dividing. We just skip that little division part. And in fact, we can even see this within this table. So looking at the loading function for a moment, we have x minus a to the negative 2. When I integrate that, I get x minus a to the negative 1. So all we did is this is minus 2 plus 1 is minus 1. And same idea when I integrate again, right? I'm not dividing by anything. However, if I look at a load, let's go down to the slope load, and I were to integrate that, I have the same function, but now this becomes squared, and I'm also dividing by 2. That's our normal way of integrating. And like I said, if that doesn't make too much sense, hopefully an example, you'll see these are actually fairly simple because you just follow the table, know that one rule for integration, which 99% of the time you're going to be using this one where, all right, fine, 90% of the time you're going to be using the one where it's just like standard integration. All right, so after you have that third step, the fourth step it has to deal with the fact that when we integrate, these are still indefinite integrals, and I get these constants of integration. I'm going to have 2 constants of integration, so what I'm going to have to do is I'm going to have to get rid of those by using my initial conditions, or you might know them as boundary conditions, for our constants of integration. So those would be, those would be something like, where do you know the slope is equal to 0, or more likely, where do you know the deflection is equal to 0? You don't know the deflection is equal to 0 at supports and things like that. So let's go ahead and stop the video here, and I'm going to do 2 examples. I hope to get 2 examples in on a following video. Check out those examples. I think it'll make much more sense at that point as I walk through it, and let me know if you have any questions, comments. Thanks.